let's find the Taylor series centered at x equals 0 for some familiar functions. To begin with, we can look at the function f of x equals e to the x. So for this, we can say that the kth derivative of this function is always equal to e to the x. Because we're looking at the Taylor series centered at x equals 0, then we would evaluate these derivatives at x equals 0, which would give us 1. So recall that my formula that I'm thinking of here for Taylor series is the sum from k equals 0 to infinity of the kth derivative of f evaluated at my center, a, times x minus a to the k. And again, in this example, a is 0. So at this point, what I want to do is plug in what I'm now realizing the kth derivative of f at 0 is equal to. This would give me, so the Taylor series is then the sum from k equals 0 to infinity of 1 over k factorial times x minus 0 to the k, which I can write as x to the k over k factorial. So this is the Taylor series for e to the x when centered at 0. Just a quick check, we can look and find the interval of convergence. So if I took the limit as k approached infinity of the next term, which would be x to the k plus 1, divided by the k plus 1 factorial, times the reciprocal of the kth term. Note that this would give me an absolute value of x times the limit of k factorial divided by k plus 1 factorial, which that's the same as 1 over k plus 1. So we get 0. And again, that's always less than 1. So this means that the radius is infinity, and consequently, the interval of convergence is the whole real line. So we want to focus on now the Taylor series for e to the x centered at 0 is this. And like I said, just a little extra, we now know the interval and the radius of convergence. Now consider the function f of x equals the natural log of 1 plus x. So this one we have to do a little bit more work because we don't just have the derivatives becoming the same function. So I start with my f of x being natural log of 1 plus x. Evaluating that at the center, we find f of 0 is the natural log of 1, which is 0. Then the first derivative would be 1 over 1 plus x, which I'm going to write as 1 plus x to the minus 1. Plugging in 0, I get 1. The second derivative would then be negative 1 plus x raised to the minus 2. Evaluating that at 0, we get negative 1. And to be clear, what I'm doing here is finding several of the derivatives until I can observe a pattern to the point that I can figure out what the kth derivative of f at 0 would be. So the third derivative of this function is now positive 2 times 1 plus x to the minus 3. When I evaluate that at 0, I'm going to get positive 2. The fourth derivative would now be negative 6 times 1 plus x to the minus 4. And evaluating that at 0, we get negative 6. And I'm starting to observe a pattern here where I can see factorials. So if I want to think about what the kth derivative evaluated at 0 would be. So again, I'm more focused on that rather than as a function of x. So I'm trying to follow the pattern I'm observing here. So one thing to note is negative 6 is negative 3 factorial. 2 is positive 2 factorial. Negative 1 is negative 1 factorial. 1 is 0 factorial. And we see here that this doesn't really follow a pattern, this 0 there, but it turns out we can deal with that separately. So for the moment being, what I can see here is, first of all, it looks like factorials are involved. It looks like when I take the kth derivative, I'm really getting the k minus 1 factorial. Notice that when I took the fourth derivative, it involved 3 factorial, the third derivative involved 2 factorial, and so on. But the other thing we have to make sure we account for is the sign change. So sometimes we get a negative one and sometimes we get a positive one. In that instance, what I can do is put a multiplier in there of -1 either to the k or k plus 1 / k minus 1. Those are interchangeable. The way that we're going to decide this is if we want to have our odd numbered derivatives, so first, third, fifth, etc., do we want those to be positive or negative? Notice that when I have the first derivative and the third derivative, and likewise it would be the fifth derivative, those are positive. So I want to put either k plus 1 or k minus 1 as the exponent on -1. If I had put k, that would instead make the second and fourth and sixth derivatives and so on positive. So this is my general derivative evaluated at 0. From that, I can find the Taylor series. And maybe what I should have set up here is that this pattern holds for k greater than 0. So we might have to worry about the k equals 0 term separately. However, notice that that is just evaluating to 0. So that means that that constant term is 0, which means that we can leave it off altogether. So while a Taylor series does start at k equals 0, when my first term is 0, that means that I can start it at k equals 1. So the Taylor series is then the sum from k equals 1 to infinity. And again, I just want to highlight that normally it's starting at 0. However, this is because the k equals 0 term is 0. And what we have to do is, again, I already have part of this definition fixed, where we would put this, and we have to fill in the kth derivative of f evaluated at 0. That's what we found above. So we have this. We can simplify this. In particular, we can simplify the ratio of factorials that I have here. If I have k minus 1 factorial divided by k factorial, that will cancel to just a single factor of k in the denominator. So this simplifies to the sum from k equals 1 to infinity of -1 to the k plus 1 times x to the k divided by k. So this is now the Taylor series centered at 0 for the function natural log of 1 plus x. Like we did above, we can consider the interval of convergence for this. To do so, we would look at using the ratio test to first find the radius. So taking the next term and multiplying, so this should actually be to the k plus 2, multiplying by the reciprocal of the kth term. First of all, the -1s we can disregard because of the absolute value. We are going to be able to factor out the absolute value of x. And what's left is k over k plus 1. That limit is 1. So we get absolute value of x. And again, we want to make that less than 1 in order to converge by the ratio test. That's already in the form absolute value of x minus a less than a value. So I know that the radius here is that number 1 on the right-hand side. Because my center is 0, knowing that the radius is 1, I know that my endpoints are -1 and +1. So in order to find the interval, we need to check those endpoints. To check the endpoints, that means that we substitute each one back into our series. So instead of x, I'm going to put in -1 here, and this is k. So think about what this simplifies to up here. So I have -1 to the k times -1 to the first times -1 to the k. And that's going to be -1 to the 2k times -1, combining my two -1 to the k's. -1 to the 2k is always positive because you have an even exponent. So this is just telling us that in fact, that numerator simplifies to just -1. So this is effectively putting the negative outside. This is simply -1 times the harmonic series. So because the harmonic series diverges, if we have every term negative, that too would diverge. So this is, you can reference the harmonic series, or that this is a p series with p equals 1. When we look at x equals 1, go back to the original series, replace x with +1. 1 to the k is just 1, so I can leave that off altogether. Now this is an alternating series. We can check the conditions of the alternating series for this. So that's that 1 over k goes to 0, and that the terms are decreasing in size, which is true as 1 over k plus 1 is smaller than 1 over k. So this series converges by the alternating series test. So this means that the interval of convergence for this series does not include the left endpoint, but it does include the right endpoint. Now let's look at the function cosine of x. So again, our goal is to find the Taylor series for this function centered at 0. So we start off with f of x, which is cosine of x. Evaluating that at 0, we get +1. F prime of x is minus sine of x. Evaluating that at 0, I get 0. The second derivative is minus cosine. If we plug in 0, that will leave us with -1. And the third derivative is now positive sine. If I plug in 0, that will give me 0. And this is actually enough, because once I've done this 4 times, I can see that this pattern that I've developed repeats. The fourth derivative would take me right back to cosine. So I'm starting to see that those coefficients will be 1, 0, -1, 0, and so on. So I want to be able to come up with a pattern here. So this pattern repeats. Let's think about what that means about the Taylor series. So one thing we haven't encountered yet is how to deal with a situation in which every other coefficient is 0. So this is a situation where I need to express my Taylor series in a way that I don't have any odd odd derivatives. So first derivative, third derivative. So I don't want to have any odd powers of x. So if we think about the way the Taylor series is represented, again, I want to write it in sigma notation, but maybe to help me get there, I'm going to think about my formula. So f of 0 represents the constant term. Then we would have plus 0 times x plus -1 over 2 factorial times x squared plus 0 times x cubed. This pattern would continue, so we'd have 1 over 4 factorial x to the 4th plus 0 times x to the 5th, and so on, which would simplify to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So how do we put this in sigma notation? Well, what we can consider here is that I have alternating sign on these terms, and instead of writing k factorial and x to the k, I only want to represent even k's. I can accomplish that by putting a 2k instead of a k in there. And notice that the exponent matches the factorial that we're taking. And likewise, now I can come back and consider the alternating sign. When k is 0, we would get x to the 0, so we'd get our constant term. When k is 1, we'd get x squared, and so on. So I see that in this case, with the negatives, I want to have a positive term when I have even values of k, and I want to have a negative when I have odd powers of k. That I can accomplish with just -1 to the k. So this is my Taylor series. Again, if we were to consider the radius and interval of convergence, we would look at the limit as k approaches infinity. The next term would be -1 to the k plus 1, x to the 2k plus 2 over 2k plus 2 factorial. Multiplying by the reciprocal of the kth term, we would get this. Now, a couple of things to consider. We can ignore the -1s because of the absolute value. I would have 2 extra factors of x in absolute value to bring out because of the 2k plus 2. And in dealing with these factorials, again, remember that what I want to do is express 2k plus 2 factorial as 2k plus 2 times 2k plus 1 times 2k factorial. So I can see that I can cancel the 2k factorial from top and bottom. So this leaves me with x squared times the limit as k approaches infinity of 1 over 2k plus 2 times 2k plus 1, and that goes to 0. So again, we get this scenario where it's always strictly less than 1, which tells me that the radius of convergence is infinity, and the interval is yet again the whole real line. So this matches with what we found for e to the x. And for one last example here, what I'd like to look at is the same process, but not focusing on the center being 0. We'll note that a lot of the times in this course, we will end up focusing on these Taylor series centered at 0. But I want to make sure it's clear how we would find the Taylor series if we were asked to find one that's in fact not centered at 0. If I go back to my formula at the very beginning up here, this is changing the value of a. So not only will it change this x minus a factor, we also then evaluate our derivatives at whatever the center point is. So to see this, let's find the Taylor series centered at x equals -1 for the function f of x equals 1 over x squared. So in my formula for the Taylor series, I'm going to consider a to be -1. So now I start with my function, which I'm going to write as x to the -2. We now want to evaluate this not at 0, but at our center, which is -1. So if I plug that in, I'm going to get +1. The first derivative of this function is -2x to the -3. If we plug in -1 for that, we are going to get a +2. The second derivative would be +6 x to the -4. If we plug in -1 for that, we get a +6. The third derivative would be -24 x to the -5. If I evaluate that at -1, I get 24. So notice that in this case, all of our coefficients seem to be positive. When I have a negative coefficient, we also have x raised to an odd power. And plugging in -1, that will be negative. So the two negatives multiply together to become positive. And so I'm starting to observe a pattern. And again, I want to observe that this is 4 factorial. This is 3 factorial, 2 factorial, and 1 factorial. So if I'm trying to get to a point where I can find the kth derivative evaluated at -1, I want to follow that pattern and notice that I'm always getting a positive term with a factorial. Now let's think about how that factorial connects to which derivative we're taking. When I found the third derivative, it was the 4 factorial. When I found the second derivative, it was 3 factorial, and so on. So it's actually going to be k plus 1 factorial. Now, putting this into our definition, this tells me then that the Taylor series is the sum from 0 to infinity. And again, things that go into the Taylor series always are the, so negative one here, these pieces here. What I have to substitute in here in the numerator is what we found the kth derivative evaluated at -1 to be. We found that was k plus 1 factorial. Plugging this in and now kind of simplifying, k plus 1 factorial divided by k factorial is just k plus 1. Likewise, x minus a -1, I can write as x plus 1 to the k. Now, like I did above, we could go through and find the radius and interval of convergence. Suppose in this example, just as it's stated, I just want to find the Taylor series. We've done that. We'll see that the reason that I went ahead and found the radius and interval of convergence for the ones above is that the first 3 that I did here are going to be examples that we really want to remember, and it will be helpful to recall when they converge. We will talk in a later video about how to use familiar Taylor series to come up with formulas for other ones. And in order for that to be useful, we want to have a collection of what we're going to consider familiar Taylor series. These first 3 that we looked at are going to be among that collection.